Right, so we're going to go over the midterm exam, and there were 5 questions plus 4 extra credit problems. So let's start. So in problem number 1, we begin with a homogeneous differential equation, y prime plus 7y equals 0, and which is the same as, again, there are many ways to do this. They're all essentially the same. It's the same as y prime equals minus 7y. So you actually, you know from calculus that the general solution is any constant times e to the minus 7x. Oops. E to the minus 7x. So that's part A. Find the general solution of the homogeneous equation. For the non-homogeneous differential equation, y prime plus 7y equals 5. So one method is, first of all, of course, there is a general formula, which if you remember, you remember, and always works to, in principle, solve a first order equation. But if you don't remember it, you could say, look for a function y, which is some unknown function u, times a particular non-zero solution of the homogeneous equation. So we want to look for a solution of the form u equal e to the minus 7x. In that case, if you differentiate it, y prime is u prime e to the minus 7x minus 7u e to the minus 7x. So y prime, and this, of course, this is y. This is u prime e to the minus 7x minus 7y. So we get that y prime plus 7y is u prime e to the minus 7x minus 7u e to the minus 7x plus 7 times y plus 7u e to the minus 7x. And of course, these cancel. This is just equal to u prime e to the minus 7x. And that's supposed to equal 5. So we just have to find a function u that satisfies this. That is, u prime is 5 e to the 7x, which means, so we're just looking for the antiderivative. U is the integral of 5 e to the 7x dx. If you integrate 5 e to the 7x, you get 5/7 e to the 7x plus a constant. That's what u is. And so y, which is u e to the minus 7x, is 5/7 e to the 7x plus a constant times e to the minus 7x. E to the plus 7x times e to the minus 7x, that's just 1. So this is 5/7 plus c e to the minus 7x. And that is the general solution of the inhomogeneous equation. And finally, we have the initial value problem associated with this. Solve the differential equation, find the solution of the differential equation that satisfies the initial condition y of 0 is minus 2. So if y is 5/7 plus c e to the minus, this should be 7x, e to the minus 7x, y of 0 is 5/7 plus c times 1, when x is 0, this is 1, equals minus 2. So c is equal to minus 2 minus 5/7, which is minus 19 over 7. So for the initial value problem, the solution is y equals minus 19. Sorry, let me write it in this one. Y equals 5/7 plus C, which is minus 19 over 7, e to the minus 7x. And this is a solution of the differential equation. And when x is 0, y is 5 minus 19 over 7. That's minus 14 over 7, or minus 2. So everything works out nicely. Any questions about this? Okay, that's problem number 1. What about problem number 2? So problem number 2, we have the differential equation xy prime minus 3y equals 0. And we always like the coefficient of y prime to be 1, so we want to divide by x. So for x either greater than 0 or x less than 0, right? That means for x in the open interval from 0 to infinity, or x in the open interval from minus infinity to 0, which you can't divide by 0, you get y prime minus 3 over xy is 0. And again, there are always multiple ways of solving this. This is y prime equals 3 over xy, or y prime over y equals 3 over x. So this equation is separable. All the y's are on the left, all the x's are on the right. Okay. So the integral of y prime over y is the log of y. And that's the integral of 3 over x, which is three log x plus a constant, or log of x cubed plus a constant, because 3 log x is a log of x cubed. So y is if you exponentiate e to the k x cubed. So y is some constant times x cubed, and this is either for, well, for x different from 0, either for a positive x or for negative x. And let's just check that this solution of the homogeneous equation is correct. If y equals cx cubed, y prime is 3cx squared, xy prime is 3cx cubed, so xy prime minus 3y is 3cx cubed minus 3 times cx cubed, which is 0, so this checks. So that's the solution. That's the solution for the homogeneous equation. Okay. Part B. So part B is to find the general solution of the non-homogeneous equation, xy prime minus 3y equals minus 6, or y prime minus 3 over xy equals minus 6 over y. And again, if we take y1 equal to x cubed is a solution of the homogeneous equation, y prime minus 3 over xy equals 0, then we look for a function u, so that y equals u times y1, which is u times x cubed, solves the equation, right? And as we take a solution of the homogeneous equation, multiply it by u and see if we can solve the non-homogeneous equation. So to differentiate this, y prime is u prime x cubed plus u times 3x squared. So y prime minus 3 over x times y is u prime x cubed plus 3ux squared minus 3 over x times y, that's 3 over x, ux cubed. X cubed over x is x squared. So this is 3ux squared. And again, plus this minus this, that cancels. So this is u prime x cubed. And this is supposed to equal, minus 6 over x, I divided by x, equals minus 6 over x. So u prime is minus 6 over x to the fourth, or minus 6x to the minus fourth. If we integrate, u is the integral of minus 6x to the minus 4 dx. That's minus 6 over minus 5x to the minus 5. Oops, sorry. Minus 6 over minus 3 x to the minus 3. Minus 6 over minus 3 is plus a constant. So u is equal to 2 x to the minus 3 plus a constant. So y, which is ux cubed, is 2x to the minus 3 plus a constant times x cubed is 2 plus cx cubed. And that's the answer. Y equals 2 plus cx cubed is a solution of the non-homogeneous differential equation. Any questions about that? All right. Number 3 is a nonlinear differential equation of the first order. Problem number 3 is y prime equals y times 1 minus y. And this equation is separable. 1 over y times 1 minus y times y prime equals 1. If we integrate y prime over y times 1 minus y, what do we get? Well, this looks like something you should integrate by partial fractions. If you have 1 over y times 1 minus y, you would try to write that as the partial fractions in the denominator will be y and 1 minus y. So this is the same as 1 over y plus 1 over 1 minus y. In fact, 1 minus y plus y, yeah, exactly. Or if you prefer, I prefer to have y first. This is 1 over y minus 1 over y minus 1. So this is the integral of 1 over y minus 1 over y minus 1 dy. This is the log of y minus the log of y minus 1, which is the log of the quotient y over y minus 1. And the integral of 1 is x plus a constant. So we get that the log of y over y minus 1 is x, I'll call this k, plus a constant k. So y over y minus 1 equals e to the x plus k. E to the k is like a constant c, c e to the x. And notice we're dividing by y and 1 minus y. So you cannot have y equal to 0 or 1. So we can only look for solutions on the infinite interval from 1 to infinity, the infinite interval from minus infinity to 0, or the finite open interval from 0 to 1. Right? And on any of those intervals, this is a solution of the differential equation. Let's solve for y, though. This is y equals y minus 1 c e to the x, which is y c e to the x minus c e to the x. So if I rearrange this, I get y c e to the x minus 1 equals c e to the x. So y is c e to the x over c e to the x minus 1. Or if I want to divide by c e to the x, I get 1 over 1 minus 1 over c e to the minus x. And again, 1 over c is just another constant. So let's just say y is 1 over 1 minus c e to the minus x. So this is the general solution of the differential equation. Let me summarize that. So in problem 3, for the differential equation, y prime equals y times 1 minus y, we have solutions which can be different on 3 different intervals. Minus infinity to 0, open, 0 to 1, or 1 to infinity. And a solution, the general solution of this equation is y equals 1 over 1 minus c e to the minus x. What about, so that's part A, the general solution. What about the initial value problem? This is part B. Y prime equals y times 1 minus y. And we want the initial condition, y of 0 equal 2, to be satisfied. But if you let x equal 0 in the expression for y of 0, which is supposed to be 2, is 1 over 1 minus c e to the 0. E to the 0 is 1. That's 1 over 1 minus c, which means 1 is equal to 2 times 1 minus c, or 2 minus 2c, which means 2c equals 1. C equals a half. So the particular solution of my differential equation is y equals 1 over 1 minus a half e to the minus x, or if you write, it makes absolutely no difference. It's 2 over 2 minus e to the minus x. And again, when x is 0, this is 2, and that's the solution. So this is the general solution, and this is the solution of the initial value problem. And for this differential equation, what happens is x gets larger and larger. The limit as x goes to infinity of y of x is the limit as x goes to infinity of 1 over 1 minus a half e to the minus x. But as x goes to infinity, e to the minus x goes to 0. So this limit is 1. Any questions about that? Okay. Let's look at problem 4. Find the general solution of the second order linear differential equation, y double prime minus 10y prime plus 24y equals 0. So we have to look at the associated quadratic equation, r squared minus 10r plus 24 equals 0. Of course, this factors into r minus 4 times r minus 6. So there are two solutions, r equal 4 and r equal 6. So for this equation, we have two exponential solutions, e to the 4x and e to the 6x. And the general solution is any linear combination of these. Y equals C1 e to the 4x plus C2 e to the 6x. Okay. In part B, we have another linear differential equation, y double prime plus 10y prime plus 26y equals 0. And very similar to this, except 24 is now 26. So the associated quadratic equation is r squared plus 10r plus 26 equals 0. And I don't see any way to factor this, so let's just use the quadratic formula. R is minus b plus or minus the square root of b squared minus 4ac over 2a, which is minus 10 plus or minus the square root of 100 minus 104 is minus 4 over 2, which is minus 10 over 2 is minus 5. Square root of 4 is 2. So this is 2 times square root of minus 1. 2 over 2 is 1, plus or minus I. So we have two roots of the quadratic, minus 5 plus I and minus 5 minus I. And we know from the elementary theory of constant coefficient linear second order homogeneous equations, one solution is e to the minus 5 x cosine x, and the other solution is e to the minus 5x sine x, and any linear combination of them is a solution. So this is the general solution of the second order equation. Any questions about that? All right. Let's look at question 5. So we have a differential equation, ay double prime plus by prime plus cy equals 0. A, b, and c are constant. And we know always what the solutions of this equation are. So you look at the quadratic ar squared plus br plus c equals 0, and this will have two roots, r1 and r2. They can be two distinct real roots. You can have a double root, two equal real roots, or a pair of complex conjugate roots. So if you have a repeated root, if r1 equals r2, the solution is, let's call this r, e to the rx, and x e to the rx. When you have a repeated root, r, the solutions are e to the rx and x e to the rx, and any linear combination of them. So for a repeated root, this is the solution. And r can be positive, negative, or 0, but if r is negative, so let me just write r1 equal r2 is minus r, so it's emphasized that this is negative, we get a solution of this form. And what is the limit as x goes to infinity? E to the minus rx goes to 0. And you know from calculus, you can use L'Hopital's rule if you don't remember, that this also goes to 0. So if you have a repeated negative root, the limit is always 0. The alternative is you have two roots with negative real part. Now, let me take a bigger piece of paper. So again, we're in this situation. We have, this is problem 5. Ay double prime plus by prime plus cy equals 0. And let's say r1, r2 are the roots of the quadratic ar squared plus br plus c equals 0. So in the first case, we're considering r1 equals r2 is some negative number. It's a repeated negative root. And we have the general solution is c1 e to the minus rx plus c2x e to the minus rx. And the limit of this as x goes to infinity is 0. In case 2, r1 is different from r2, and it says negative real parts. So there, let's say 2 subcases. So case 2a, r1 and r2 are real negative numbers. Or there's minus r1, minus r2. These are real negative numbers. In this case, your fundamental solutions are e to the minus r1x, e to the minus r2x. r1 and r2 are different. The general solution is any linear combination of these. And because this is an exponential to a negative exponent times x, again, as x goes to infinity, this goes to 0. And the third case, or the second subcase, if you like, is R1 and R2 are complex numbers, not real. So, but then they occur in complex conjugate pairs, and you get a solution, let's say, and with real part minus R. So let's say R1 is minus R plus I times S, and R2 is minus R minus I times S. And your solution is going to be, one fundamental solution is e to the minus R x cosine Sx, and e to the minus Rx sine of S times X. And the general solution is any linear combination of these. And again, as x goes to infinity, since e to the minus Rx, this is a decaying exponential, this is just oscillating between plus and minus 1. This also goes to 0 as x goes to infinity. So if you have a constant coefficient, second order homogeneous linear differential equation, every solution goes to 0 if you either have a negative repeated real root or a pair of roots whose real part is negative, either two negative numbers or two complex numbers with complex conjugate numbers, negative real part. That is problem 5. Any questions about this? Okay. So let's look at the extra credit problems. So extra credit. Problem 1. We have an equation y prime equals 4y plus 3x over x. And again, you can do this in several ways. This is a linear equation, but it's also a homogeneous equation in the sense this is 4 times y over x plus 3. So we can look for a solution y equals u times x, in which case y prime is u prime x plus u. And so y prime, which is u prime x plus u, is supposed to be 4 times y over x. That's 4u plus 3. So xu prime equals 3u plus 3, where u prime is 3 over x times u plus 3 over x. So this is a ordinary, usual that is, first order linear differential equation that we have to solve for u. So let's proceed to do that. If you look at the complementary equation, y prime equals 3 over, u prime equals 3 over xu, then u prime over u is 3 over x. So the log of u is 3 times the log of x plus a constant, or log of x cubed plus a constant. So u is some constant. If you exponentiate, you get c x cubed. And y is u times x is c x to the fourth. Let's see if this is correct. Let me check. So if y is cx to the fourth, then y prime is 4cx cubed. And 4y plus 3x over x is 4 cx to the fourth plus 3x over x equals 4cx cubed plus 3, which is y plus 3. So this is y. So y prime is y plus 3. But something isn't right here. So let me go back and check what I did. So y prime is 4y over x plus 3. So one way to do this is to observe, if I divide by x, this is 4y over x plus 3. So this is a homogeneous equation in the sense that it's a function of y over x. So I'm going to let y over x equal u, or y equal u times x. In that case, y prime is u prime x plus u, and that's supposed to equal 4u plus 3, which means u prime x, or xu prime, is 3u plus 3. So u prime is 3 over xu plus 3 over x. And let me just. Yeah. I mean, I actually solved this problem in part. This is problem 2. So u prime equal 3 over ux, u equals cx cubed is let me call this u1. u1 equals cx cubed is a solution of the homogeneous equation. And I could have just solved this directly. This is essentially the same as a problem that previous problem. Let's try using this method of homogeneous equations. So if I look at the so this is my differential equation. This is the complementary equation, where you make it equal to 0. So this is the homogeneous equation. The solution of this is constant times x cubed. So I then look for a solution of this equation where u prime is some other function. Let me just call it v times x cubed. So in this case, sorry, u is v times x cubed. So u prime is v prime x cubed plus 3x squared v. And this is supposed to equal 3 over x times u plus 3 over x. So this is 3vx squared plus 3 over x. Let's see. I'm not sure why I am screwing this up so badly. Let me do it just make it a little bit easier. So cross all that out. That's like a good start. So the problem is y prime equals 4y plus 3x over x, which is 4y over x plus 3. And I want to let u be equal to y over x, or y equals u times x. So y prime is u prime x plus u. So we get y prime, which is u prime x plus u, equals 4u plus 3. So u prime times x is 3u plus 3. And we have to solve this equation. And on the or another way of writing this is just xu prime minus 3u equals 3. So we actually solved this equation in part 2, except with a 6. Instead of 3, we had minus 6. So the solution in problem 2, so there's no reason to go through it again, solution to problem 2 was of the form y equals some constant, I'll call it C1, plus cx cubed, where y of, we just have to figure out what this constant has to be. So y prime is 3cx squared, and that's supposed to equal c1 plus cx cubed plus 3x over x, which is c1 over x plus cx cubed plus 3. So I don't know why I'm screwing this up. Very strange. If you use the fact that this is homogeneous in the sense that the right-hand side is a function of y over x, the general method is always to substitute y equals u over x, y equals u times x, u equals y over x, and then you get an equation in u, which you then have to solve. So let me just solve it and forget the fact that we already did this problem a moment ago. So we have y prime equals 4y plus 3x over x, which is 4y over x plus 3. I should just make the following observation. You could write this as y prime minus 4 over x times y equals 3. And this is the usual non-homogeneous linear equation. But I want to try and solve it like this, even though it's easier to just to do it like this. But I let u equal y over x. And I want to find u. So y is ux. So y prime is u prime x plus u. So this equation becomes simply y prime, which is u prime x plus u, equals 4u plus 3. So u prime x equals 3u plus 3. So u prime is 3 over x u plus 3 over x. So if we look at the equation u prime equals 3 over x u, one solution is called u1. So this is if you let this equal to 0. One solution is u1 equals to x cubed. Because if you differentiate this, you get 3x squared. And if you divide, and if you multiply this by 3 over x, you also get 3x squared. So for this equation now, we look for a solution which is some function v times x cubed. So u prime is v prime x cubed plus v times the derivative of x cubed, which is 3x squared, plus, so that's u prime is v prime x cubed plus v times 3x squared. And this is supposed to equal 3 over x times u plus 3 over x. So this is 3vx squared. This cancels this. So we get v prime x cubed equals 3 over x. V prime is 3 over x to the 4th. So v is the integral of 3 over x to the 4th, which is minus 3/4, which is minus 1, x to the minus 3 plus a constant. So u is vx cubed. If you multiply this by x cubed, you get minus 1 plus cx cubed. And y is u times x is minus x plus c x to the 4th. So in the very unlikely event that this is finally correct, let me check. So I never believe that I do problems correctly, and I have to check them. So if y is minus x plus cx to the 4th, y prime is minus 1 plus 4cx cubed. And for y over x plus 3 is 4 over x times minus x plus cx to the 4th plus 3. This is minus 4 plus 4cx cubed. So I just have this constant wrong. Why is that the case? I have to go back and check. So y prime is 4y over x plus 3. So y prime, which is u prime x plus u, is 4u plus 3. So u prime x is 3u plus 3. So u prime is 3 over xu plus 3 over x. The solution of the homogeneous equation u1 is x cubed. So I look for a solution v times x cubed. So u prime is v prime x cubed plus 3vx squared. And that's supposed to equal 3 over x times u. So that's 3vx squared plus 3 over x. And these cancel. So v prime x cubed is 3 over x. So v prime is 3 over x fourth. So the antiderivative of 3 over x to the fourth is minus 1 over x cubed. Because you differentiate this, you get 3 over x to the fourth plus a constant. So if I multiply this by x cubed, I get minus 1 plus cx cubed. And if I multiply this by y is u times x, so if I multiply this by x, I get minus x plus cx to the fourth. So let me check that. If y is minus x plus cx to the fourth, y prime is minus 1 plus 4cx cubed. And for y over x plus 3 is 4 over x times y minus x plus cx to the fourth plus 3 is minus 4, oh, plus 3. This is my mistake. Minus 4 plus 3 is minus 1 plus 4cx cubed. So this is correct. Phew, took a while if you're bad at this, but that's the solution of this differential equation. Okay, that was problem 1. Let's see if we can do problem 2. Maybe I'll be luckier. We have the second order, the first order non-homogeneous equation, y prime plus 3x squared y equals 3x squared. And it's an initial value problem. Find the solution with y of 0 equal to 8. So if we first look at the homogeneous problem, y prime plus 3x squared y equals 0, or y prime over y is minus 3x squared, and then you integrate, you get log y is minus x cubed, but one solution is minus x cubed, or y is e to the minus x cubed, y1. So now we look for the general equation, we look for a solution of the form y equals u e to the minus x cubed. So y prime is u prime e to the minus x cubed minus 3x squared u e to the minus x cubed. And that's supposed to equal y prime, sorry, plus, that's y prime, plus, so that's y prime. So y prime plus 3x squared y is u prime e to the minus x cubed minus 3x squared u e to the minus x cubed plus 3x squared times y, which is u e to the minus x cubed. And all this is supposed to equal 3x squared. And again, these terms cancel. So I get u prime e to the minus x cubed equals this. So u prime equals 3x squared e to the minus x cubed. And so u is the integral of 3x squared e to the minus x cubed, which is exactly minus e to the minus x cubed plus a constant. So y is this times, oops, I'm off by, I always get a minus sign wrong. So y prime over y is minus 3x squared. So log y is e to the minus x cubed. So u e to the minus x cubed. U prime e to the minus x cubed minus 3x squared times this. So y prime plus 3x squared y equals 3x squared. So u prime e to the minus x cubed equals 3x squared. So u is the integral, this is a plus e to the x cubed. So it's plus equals e to the x cubed plus c. So y equals this times e to the minus x cubed is 1 plus c e to the minus x cubed. And so again, let me just check, see if this is correct, because I'm always questionable about these things. So I want to solve the initial value problem, y prime plus 3x squared y equal 3x cubed. And solving this problem, I got as my general solution, y equals 1 possibly y equals 1 plus c e to the minus x cubed. So y prime is minus 3x squared c e to the minus x cubed. So y prime plus 3x squared y is minus 3x squared c e to the minus x cubed plus 3x squared y is plus 3x squared plus 3x squared c e to the minus x cubed. These cancel, equals 3x squared. So this is the general solution. And if I evaluate this at y of 0 is 1 plus c e to the 0, which is 1 plus c, and that's supposed to equal 8. So c equals 7. So the solution of the initial value problem is y equals 1 plus 7 e to the minus x cubed. That is the solution of the problem. Okay. Good. Let's look at problem number 3. We have P and Q continuous on an open interval from A to B. And we have the differential equation y double prime plus P of x y prime plus Q of x y equals 0. And we have two solutions, y1 and y2. So y1, y2 is what is called a fundamental set of solutions. If every solution is of the form a linear combination of y1 and y2, c1 y1 plus c2 y2 for some constant c1 and c2. And we say that y1 and y2 are linearly independent. if y2 is not some constant times y1. Right? You can't write one as like 3 times the other. That's what it means to be. That's for two functions. That's what it means for the two functions to be linearly independent. Okay? That's all it is. And in problem 4, we have a set of functions, x squared minus 3 and x cubed plus 2. So what is the Wronskian? It's the determinant of the 2 by 2 matrix where x squared minus 3, the functions are in the first row. Their derivatives are in the second row. So the determinant is x squared minus 3 times 3x squared minus x cubed minus 2 times 2x. This is 3x to the 4th minus 9x squared minus 2x to the 4th plus 4x. So this looks like x to the 4th minus 9x squared plus 4x. That's the Wronskian. And this Wronskian is not the zero function. So that means that x squared minus 3 and x cubed plus 2 are linearly independent, because the fundamental theorem in this beginning of chapter 2 says that two functions are linearly independent if and only if the Wronskian is not, that are solutions of it, if and only if the Wronskian is non-zero. And it's clear you can't write, or you can just show directly, x cubed plus 2 cannot be a constant multiple of x squared minus 3, because this has degree 3 and this has degree 2. So that's it. Everything. Okay. Any questions about any of this? All right, then on Wednesday, we'll talk a little bit more about chapter 5. That is, we've dealt with constant coefficient homogeneous equations. But what about non-homogeneous equations? This is much more complicated. And we'll talk a little bit about that. And then we will move on to chapter 7 on series solutions. Okay. If there are no questions, no more questions, not any questions, then we are done for the morning. Okay, that's it, everyone. See you on Wednesday. Bye.